In this last video, we are going to discuss graph traversals. When we discuss trees, we discussed two broad categories of traversals that included breadth first search and depth first search. Within depth first search, we saw in-order, pre-order, and post-order traversals. But for the sake of graphs, we'll cover the two broad categories, which is breadth first and depth first. Within depth first, there's also like pre-order and post-order graph traversals, but there's no such thing as in-order because it doesn't make sense. So let's talk about the first one, which is breadth first search. You remember, like when we discussed trees, we were discussing that breadth first search is implemented as level order, where we had a tree like this, and we printed all the levels one by one, which is this, then this, then this, and so on. It works exactly similar in graphs, but in this case, we do not have a source vertex. So in case of trees, we always had a source called root. But when we are implementing a breadth first search or depth first search, we need to pass in the source into our method, which is BFS or DFS will take in a source vertex. And how it's going to work is it's going to print the source vertex first, which is in this case A. Next, it will print all the neighbors of A. Next, it will print the neighbors of A, which is B's neighbors are D and C. So it's just going to, so B's neighbor is just D and C's neighbor is just E. So in this case, it will print D and E next. Next, D's neighbor is C, but it has already been printed. So we need a mechanism to keep track of what has been visited and what has been not, because now we can go back and forth to different vertices. So we need a mechanism to keep track of visited and unvisited nodes. So at the next level, it's going to print D and E. Finally, like B and D has this child, not the child, but it's connected to F, which is its neighbor. So we are going to print like this value F. So this is the pseudocode for breadth first search, and we implement BFS exactly same as we discussed in trees with the help of a queue. This is the algorithm. I'm going to do a try run just on like giving you an example of valid BFS. Like this was valid BFS we saw in the earlier case. So let's do a run on this particular graph with this algorithm. So to keep track of what has been visited or what has been not, you need something called a set, or you need an array of size vertex and type boolean. So this boolean is going to keep track of whether this vertex, like let's say if we have this array or map or something like that, that stores all the vertices. We have A, B, C, D, E, and F. Initially, all of them will be false. Like this, we haven't visited these vertices. So we start with any arbitrary vertex. In this case, like let's say if we start with A or we pass in a source vertex, we place them in a queue data structure, which is we have this queue. We push A into a queue. Next, we start our algorithm with till the queue is not empty, which is exactly the same how it worked in trees. We take a vertex, which is we take out one of the first elements in the queue, which is we do a dequeue operation. We mark this as visited, which is now this false will be changed to true in this statement. Next, we are going to see like what are the adjacent values of A. So this is the exact same question that we were asking in our graph implementation, which is what are the values that are adjacent to A. So this is going to return like a vector of, like you might have a function that does this. So in our API, we had something like get adjacent, right? So you're just calling that get adjacent method. This will return the neighbors of A, which is B and C. Next, for all vertices V that are adjacent to this vertex U, so that means we have this vertex U called A, and we have V called B and C. We are going to check whether each of these have been visited or not. So B and C are not visited. So what we are going to do is we are going to mark these as visited, and we are going to push these into our queue, like one at a time. Next, this is again like repeated, which is you have B. So we are going to check what are the adjacent values of B. So D will be returned. Now, since D is not there in this entire, like in the map, this has not been visited, we are going to mark this as true, and we are going to insert D into this array. So after this, we are going to pop the value, which is, we have now finished visiting U. So you are going to take a vertex out, which is like, we have finished this B as well. Now we are going to do the same with the value C. So C has which vertices that are adjacent? It has just one, which is E. So we are going to push that E and mark it as visited. Lastly, we are going to check what are the adjacent values of D. So in this case, we have two values that are adjacent to D, which is C and F. Now, since C is already visited, like you can see the C's value is true, so it is never going to like mark this value or insert it into the queue, because otherwise we'll have like an infinite recursion or an infinite program. So we are going to pop this like similar to the earlier one. And finally, we are going to do this with E and F. Now you can print the, like, let's say if you are trying to print all of these, you can just print it right here, which is in our for loop, like in our larger while loop, like whenever we are popping an element from our queue, you can just like print it there, and it's going to do the breadth first traversal. The depth first search like is going to work pretty similar to the earlier ones, where we saw like you traverse left root right, or left right root, or root left right. In this case, it's going to like, since we do not have left and right here, like it could have like multiple children, not multiple children but multiple neighbors, which could be 100 nodes. Like A could be connected to so many different nodes. So we have this concept that we are going to use a stack data structure to implement this depth first traversal or depth first search traversal. You can also use like a recursive way to implement this, but I typically prefer the stack based implementation. So in this case, how it's going to work is, what we are going to do is we'll first print A, like let's say if that's the source. Next, we are going to go to either of its neighbors. So if we go to B, like let's say we take the shorter value, which is like we compare all these values. Since B is smaller than C, let's take this path, because let's say if we are trying to test it, there could be multiple BFS and DFS paths. So if there's a tie break, we have this set of rule that whichever has the lesser, like whichever is a lower alphabet, we are going to use that first, which is in this case, B was lower, we are going that direction. So instead of printing C here, we are going to go further deep, because that's the property of depth first search, which is after you have traversed B, instead of going to the other child of A, what you're going to do is you will keep going down, which is you will keep going to its children till you reach an end, which is in this case, like B will go to D, and now D has two choices, which is C and F. Now C is the smaller child, so it will go to C because of our tie breaking strategy. Next, C has just one child, E, so it's going to print E. Next, it will print F because E has just one child. Finally, it's going to traverse back up, which is it will go back up to like F doesn't have children, so it will go back up. Now E doesn't have any more children, so it will go back up. C doesn't have any children, so it will go back up. D doesn't have any more children, so it will go back up. B still has one more child, C. So it's going to see whether C has already been visited or not. Like since C is already visited, nothing will happen. But let's say if we didn't had this node, which was like, let's say in this particular example, if we didn't had this edge, so in that case, it's going to work something like this, which is you will print A, next it will print B. So B has one child, it will go there. So D now has just one child, F. So it will go to print F. Now F doesn't have any more children, so it will go back up. Now D doesn't have any more children, it will go back up. And B doesn't have any children, so it will go back up. Now A still has another child that has not been traversed. So it will print C. C still has one child that has not been traversed, so it will print E. And E has just one child which has not been traversed, which has already been traversed. So we are done here. So you can use the stack data structure. We are going to see the implementation of both DFS and BFS in our problem solving lecture, but this is the general algorithm.